then. Right, so this is June 2018 last question of Unit 2. Let's begin. Gold leaf electroscope is a device that can be used to detect charge. The deflection of the gold leaf depends on the amount of charge on the zinc plate and the conducting rod. This is your zinc plate which is present, and there is some charge stored on this plate, and this is your gold leaf, and the conducting rod is right over here. Okay, this is the entire rod. Now, in a demonstration of the photoelectric effect, remember the photoelectric effect, the emission of electrons using the energy from the photons of light. A teacher charged the zinc plate with negative charge and the gold leaf was deflected. The zinc plate was charged negatively. What this actually did was it repelled the electrons over here, and as these electrons in this conducting rod were repelled, and as there became excess of electrons on these two particles, on the conducting rod and the gold leaf, deflection occurred. Basically, the repulsion in between the two negatively charged rods occurred. Okay, the gold leaf, which was also became negatively charged, and the conducting rod, which also became actually not negatively charged, but rather the electrons from there, they just got deposited over here. Okay, because the other electrons, they got repelled. And so there was an excess of, or you could just, you don't need to go into that detail, just assume that there was some changes over here. There was some changes due to which deflection occurred. Now, when ultraviolet radiation of this much frequency was shown on the zinc plate, the deflection of the gold leaf was reduced. This deflection was then reduced when some ultraviolet radiation fell on the zinc plate. Now they're asking, explain why the deflection of the gold leaf reduced, and your answer should include a calculation. The work function of zinc is given to you. Now, when you incident ultraviolet radiation over here, the electrons, they'll gain the energy from the ultraviolet radiation and they'll be emitted if this energy which is incident upon this zinc plate is either greater than or equal to the work function energy. If you remember the work function energy, the work function was the minimum threshold energy needed to cause photoelectric effect. So if this ultraviolet radiation brings in enough energy, either equal to or greater than the work function energy, then photoelectric effect of these electrons would occur. And so these electrons would be removed. And as the electrons are removed, the deflection of the gold leaf would get reduced. Because as the electrons are removed, what would happen? Electron is lost. A hole will be left over here, right? A vacancy of electron will be left. And so the electrons which are present in excess over here, they'll flow towards that hole and will fill in that hole. Okay? So basically, that's the reason why this deflection reduces. So now all we need to do is just explain this. They've given us the work function energy. If you look at the frequency of the ultraviolet radiation, we can use this to calculate the energy of this radiation which is coming in, the incident radiation. So energy of the photon which is incident upon the gold plate, sorry, the zinc plate, energy of the photons of ultraviolet radiation, ultraviolet, is equals to HF. H is the Planck's constant, which is 6.63 raised to the power of minus 34. The frequency given to you is 2 raised to the power of 15. And the energy that this gives us is how much? Can you calculate this, please?
The 4.6 into 10 to the power of minus 52.
Minus?
52.
It's not 52. This is negative 34 and this is positive 15. I think you didn't put in. Yeah, this is positive 15. See? They didn't give us a negative sign here.
For work function for zinc, which they gave 6.9 into 10 to the power minus 10.
That's the answer? The answer to this is 6.9 raised to the power of minus 19, or what? Now, this is the energy of the photons which are incident. Compare this energy with the work function of energy. The work function of zinc, actually, sorry. The work function energy of zinc is 6.9 raised to the power of minus 19 joules. And this energy of the photons of ultraviolet radiation, the energy of UV radiation, is 1.3 raised to the power of minus 18 joules. Is this greater or lesser than the work function energy? Definitely this is greater. So if the energy of the incident photons is greater than the work function energy, then yes, photoelectric emission would occur, or photoelectric effect would cause the electrons to be emitted. Photoelectric effect would occur from the zinc plate.
Oh, okay.
And so electrons would be reduced. And if electrons are reduced, then deflection reduces. And by the way, this gold leaf electroscope is actually used for detection of charge. It's just used for detection only. What does the marking scheme say? Well, they use E is equals to HF and got this energy. Photon energy is greater than the work function. So electrons have sufficient energy to release the electroscope. So electroscope loses charge. Or you could say it is greater, so it loses charge. Loses charge. Loses charge is the underlined key term. We cannot afford to lose this term, so we have to use it as well. So electrons would be reduced from that. Also means the same thing, but okay, we will get marks, we will get full marks for this answer, but the better term to be used instead of the electrons would be that the electroscope loses charge, because that's the underlined term. Electroscope loses charge, okay, as a result of the photoelectric emission. Now, explain what would be observed with the gold leaf electroscope if the ultraviolet radiation of the same frequency but lower intensity was used. Okay, frequency is the same. Energy of a photon is equal to HF. Okay, if energy of the photon is this much and the frequency is the same, then the energy of every photon is gonna stay the same. Energy of photon is the same. Now, if energy of the photon is the same but the intensity is reduced, so let me tell you something, the intensity is actually equal to the total number of photons which are reaching there per unit time multiplied by energy of a single photon. Okay, that's the intensity's formula. Okay, intensity is basically the energy per unit time which is reaching that area. So we can write it in the following way: the number of photons reaching there, a number of photons falling on the surface per unit time, incident per unit time, multiplied by energy of a single photon, which is this much. So now every photon that is coming and that is being incident on that surface of zinc, it will release out one electron. So for every photon, you'll get one electron. Okay, and the frequency of every photon should be high enough to cause that emission. The frequency of every photon should be greater than the threshold frequency, or I can say that the energy of every photon should be greater than the work function. So if the frequency is not changing, frequency is the same, the energy is not changing. And if the energy is not changing, then that means photoelectric emission will still occur. But since the intensity has now reduced, that actually means the number of photons which are arriving there have reduced. If the number of photons have reduced, then that means the number of electrons which are emitted will also be reduced. Electrons emitted per unit time will be reduced. Emitted per unit time is reduced. So we can say that the rate of loss of charge is reduced. And if the rate of loss of charge is reduced, then will the gold leaf reduce the deflection quickly or slowly? It will reduce its deflection at a slower rate. So gold leaf reduces deflection slowly, because the rate of loss of charge has now reduced. So the rate of decrease in deflection also reduces. Clear?
Yeah.
Let's verify this. Every photon interacts with every electron. Okay, we did mention this, that every photon will remove out one electron. Frequency is the same, so energy will stay same. At lower intensity, fewer photons per second. Okay, I also said the same thing. Number of photons reaching there per unit time means the same thing. And then the gold leaf's deflection would reduce more slowly. So we got all the 4 points. And this is a very typical answer. It is quite repeated, meaning not in terms of gold leaf every time, but these 3 points are very frequently asked. That what will happen when the intensity reduces, keeping the frequency constant. So in that case, the number of photons which are coming will reduce, and so the number of electrons emitted will also reduce. But what happens if the if the frequency is reduced, keeping the intensity constant? Then what would happen? If the intensity is kept constant and the frequency has reduced, this actually means that the energy of every photon has now reduced. And if this frequency has become less than the threshold frequency, that means that the energy of every photon has now become less than the threshold energy. Then in that case only, no emission would occur, even if the intensity is the same, even if the total energy which is reaching there is the same. Since the frequency of every photon has reduced, therefore the work function, the energy of every photon would become less than the work function energy, and no electrons would be emitted due to photoelectric emission. No photoelectric emission would occur. This also proves the particle nature of light, because if the light was behaving as a wave over here, then constant intensity would have meant that after a certain period of time, emission would have occurred. But no, emission does not occur even after a certain period of time. So this proves that light has a particle nature as well, in addition to the wave nature. Okay. In the early 20th century, the wave model was generally accepted as an explanation for the nature of light. Explain why the wave model cannot explain the photoelectric effect. See, the same question has been asked over here. If the light was acting as a wave, then wave did not need any threshold frequency. Threshold frequency was not needed. Even if a light of a lower frequency, let's say the threshold frequency is f0, okay? Even if you have a light of half f0, meaning half of that threshold frequency, even if this light in the form of wave was incident upon the electrons over here, then what would have happened? After a long period of time, the electrons would have absorbed enough energy to be emitted out. But this does not happen over here. Over here, as soon as the photon of light, comes and hits the electron, which is over here, with sufficient frequency or sufficient threshold energy, or with sufficient work function energy, or with sufficient energy that is greater than the work function energy, instantaneous emission of 4 electrons occur. So electrons are either emitted or they are not emitted at all. When are they emitted? They are emitted when the energy of this incident photon is greater than the work function energy. But when are they not emitted? When this energy of the incident photon is less than the work function energy. So Instantaneous emission of electrons occur when this energy is greater than the threshold frequency, than the work function energy, and this cannot be explained using the wave model because waves require a delay. Okay, waves require a certain time for absorption and then emission, even if the frequency of that wave was lower. But if you use a lower frequency for photoelectric effect, the photoelectric effect never happens. It never happens. Okay, so this ensures that photons of light are acting as particles which come and collide against the electrons and so cause the electrons to be emitted out instantaneously. That's the explanation. Let's go through the marking scheme now. It says electrons are released instantaneously even at low intensity. Okay, intensity is a different thing, frequency is a different thing. Intensity is the number of photons multiplied by HF, the energy of a single photon. Frequency is over here. And energy is dependent upon the frequency and it is not dependent upon the intensity. There is a minimum frequency for releasing the electrons, the threshold frequency. Remember, we've talked about it. If the frequency of the photons is greater than the threshold frequency, only then will the photoelectric effect occur, otherwise it will not happen. More intense light does not increase the kinetic energy of the electrons. Okay, we missed out this point. What does this mean? Well, this actually means that the photons which are coming and hitting in the electrons, some of that energy is used in causing the photoelectric effect, and the remainder of this energy is converted into the kinetic energy of the electrons which are emitted. So these electrons' kinetic energy does not increase if the intensity is increased, but rather it only increases when the frequency is increased. So this also proves that where do the electrons get their energy from? They get the energy from the colliding photons. And there's a maximum kinetic energy of electrons for every specific frequency. Meaning, if you increase the frequency, the kinetic energy increases. That's the point which has been explained over here. So even if the frequency, and given that these frequencies are greater than or equal to the threshold frequency. Okay, so these are the 4 points you must, okay, any 3 of these are needed for your answer. So we did mention the first 2, the third or the fourth one, you could choose to mention any of these 2. So more intense does not increase the kinetic energy, and that's actually understood because photons themselves are particles, and these particles, when they collide against the electrons, they'll transmit their energy to the electrons instantaneously. Some of it will be used to overcome the electrostatic forces of attraction from the nucleus and what cause the photoelectric effect, and the rest of it will be converted into the kinetic energy of this electron. And the maximum electrons, maximum kinetic energy for a specific frequency. There's a maximum kinetic energy for every specific frequency, or in wave model, there is no maximum kinetic energy of electrons for a specific frequency. Specific frequency means that every frequency has its own maximum kinetic energy, meaning every frequency has its own energy, and if all of that energy gets converted into kinetic energy, that kinetic energy becomes the maximum kinetic energy, given that some of it has already been used to overcome the work function energy. Clear?
Yeah.
Don't worry, I have a whole topic on photoelectric effect as well, so I'll send in that lecture to you. Watch that. Over there, I've explained it in detail why the photons, they exhibit particle nature and not the wave nature. Okay, and I'll tell you the points, the timeline which you need to view, and the rest of it is not relevant to you, so you can skip the rest of it. Okay, I'll try sending it today. Okay, this is now my unit 3 that we're going to start. Okay, unit 3 practical. So here we go. Any question before I move on?
No.
Okay. Right, this is our unit 3. Okay. So which of the following is the SI base unit? SI base unit. Ampere is an SI base unit. Yep, that's the SI base unit. In an experiment to determine the Planck's constant, a student uses a wavelength of 431 nanometer. Which of the following is the correct value of inverse of wavelength? Inverse of wavelength meaning 1 upon 471 times of, okay, the nanometer can be left or it can be converted as well. So let's do this, both of them. So can you give me the answer to this?
Why is it 10 into -9?
Because there is an n over here, n means nano, nano means 10 raised to the power of -9.
Uh,
Yep.
2, 1, 20, wait, 1, 2, 3, 4, 5, 6. 2.1 into 10 to the power of 6.
Okay. Basically, you don't need to count it. There's on the left side of your calculator, if you look at it, there's ENG number, ENG button. Just click that. It will give you in terms of 10 raised to the power 6 as well.
I didn't know this. Okay, thank you, sir.
Okay. And but it's actually, it would have been 212 raised to the power of 4 over there. So you need to convert that further, okay, into this. So it's 212 raised to the power of 6 per meter, okay, per meter. So option D should be the correct answer. Let's keep verifying it as well, side by side. Yep, that's the answer. Okay, this is all that into 10 to the power of 6, but this is nano over here, so you don't need, the nano has already been taken care of, so you don't need to consider that again. A student has a sample of material in the form of a wire with a diameter of about 1 millimeter. To determine the resistivity, which of the following quantities would not be needed? Resistance is equal to rho L upon A. Resistivity needs to be calculated, so RA upon L. You need the resistance, area, and length. So resistance is needed, area is needed, length is needed, the density is not needed. Option A is your answer. Clear?
Yeah.
Which of the following instruments should the student use to measure the diameter of a wire? You have a wire, wire's diameter is quite thin. C, micrometer screw gauge. Yep, that's the answer. 5. Which of the following is a base unit of resistivity? It's ohm meter. Or you could use that formula, rho L over A, and then rearrange it and get your answer. Clear?
Could you rearrange it and get the answer?
Okay. So just make rho the subject. So it's going to be R,
RA over N.
and R is ohm, A is meter squared, L is meter. So meter and meter squared, the square cancels out. What is left? Clear?
Right.
Okay. Oh, we are done with the MCQs. Quite quick. Experiment report states that the mean diameter of a nylon thread is this much. Okay, 0.150 millimeter plus minus 0.005 millimeter. Okay, you've been given your measured value and its absolute uncertainty. State the range of measurements. Okay, you just need to write down the upper limit and the lower limit. Add 0.005 to it and subtract it. It's gonna be, when you add it, it's gonna be 0.200,
155.
and when you subtract it, it's gonna be 0.100.
When you add it, it's going to be 0.155.
Oh, my bad. 155, then what's this? Sorry, this is not 0.100. When you subtract it, what is it? It's 0.145.
145.
All right. That should be the answer. Yeah, that's the answer. Okay, 3 decimal places is a must, okay? And actually writing it from the smaller to the bigger is a more preferred way of writing it, but that one is also acceptable. Okay, this is a preferred way of writing it, but this is also acceptable. Calculate the percentage uncertainty in the measurement of diameter. So calculation of percentage uncertainty, easy. How can you calculate it? What's the formula of calculation of percentage uncertainty?
Percentage error over
Uncertainty, or the error, divided by the measured value multiplied by the 100%. So what's the error? What's the measured value? Multiplied by 100, give me the answer. What's the answer?
3.33.
3.33%. Give it to three significant figures. Okay, because these are three. Wait, this is one and this is three. Three is fine. Where is it? One or two significant figures. Okay, then you wait. They've given it to three significant figures or seven. One or two significant figures, not three. Okay, so basically the rule over here is the following. You look at these two, the numerator and the denominator, the significant figures in the raw data, and you look at the number which has the fewer number of significant figures. So the numerator has fewer number of significant figures. You have one significant figure over here. So your final answer should either be one significant figure or one more than this, so or two significant figures. Okay, that's the basic rule, especially in practical when you are writing down your final answers. It's going to be 3.3%. Okay, or you could leave it to 3%. Doesn't matter. Clear?
Yeah.
Value from half range or full range, 3% or 7%. Both of them are accepted. Okay. The report states that the mean diameter of the human hair has a measured value of this much with a percentage uncertainty of 5%. Calculate the uncertainty in measurement of the diameter of the hair. So you need to find out the uncertainty. You know the percentage. So just take out that percent of the measured value. So 5% of the measured value, 0.075. What's the answer? What's the uncertainty?
2.75 into 10 to the power of minus 3.
Okay, but I'm not going to write it over here in this form. We've been given two significant figures. So I would prefer writing it to two significant figures, 2.8 raised to the power of minus 3. What did the marking scheme say? Yeah, they've also done the same thing. Wrote it to two significant figures. Okay. Wait, they've written 3.8. Is it 2.8 or 3.8? It should be 3.8, not 2.8.
It's 3.75.
Can you please recheck it? Because they've done the same.
Yeah, it was 3.75.
Oh, 3.75. All right, great. Moving on. Question 7. A student is to determine the viscosity N. Okay, this is the coefficient of viscosity of a liquid using a falling steel ball, spheres, and graphical method. Oh, I remember doing this experiment. There was a long glass cylinder, and then we had oil inside of it. A long glass cylinder, which was filled with oil, and then there was a rubber mass over here made out of clay, actually clay mass, which was somewhat cylindrical in shape. And then what we did was we just dropped it in the oil, and then it went down and hit the base slowly. Of course, it didn't break the glass cylinder. And then we measured the time it took for it to fall this length, and the length was measured using a ruler, or the length was measured using the markings on the cylinder. And then we had the length, we had the time, we had the length, time, and stopwatch. We used it to calculate the coefficient of viscosity by drawing out a graph. Of course, an equation was already given to us. Okay, so let's read through this question. This shouldn't be that difficult. Okay, so the student has a measuring cylinder filled with liquid and some steel balls, steel spheres of different diameters. All right, we've got steel spheres. Then they're saying that there is terminal velocity v of a sphere falling through this liquid is given by this expression. Okay, we've got this expression for the terminal velocity, which is equal to 2 times r squared times rho s minus rho l into g divided by 9 times eta. Eta is your viscosity, coefficient of viscosity, where r is the radius, rho s is the density of the steel, rho l is the density of the liquid, and the values of both rho s and rho l are known. Write a plan for this experiment. Okay. They've even given us the steps to do this, so this shouldn't be that difficult. We need to draw and label a diagram showing the apparatus that we will use, list any additional measuring instruments that are not shown in the diagram, list the quantities to be measured, find two quantities listed in C, and explain your choice for measuring instrument. Okay, the steps are exactly the same for the one which we did in the previous experiment. State which is the independent and dependent variable, one quantity, comment on whether the repeat readings are appropriate, explain how the data is collected to and used to determine the viscosity, including a sketch of the expected graph, and then identify the sources of error and uncertainty and comment on the safety finally. Okay, so let's start out from their plan. We need to draw out and label a diagram showing how the apparatus will be used. Okay, so we need to determine the terminal velocity of a sphere falling through the liquid as shown over here. Okay, so we've got the radius of the sphere, the r over here. So to measure the radius, what would we require? We would require either a micrometer screw gauge or a vernier caliper, right? I'm gonna use a micrometer screw gauge. Then the density is already known, so we don't need to measure that out. N is what we need to calculate, but we don't need the term. We don't know the terminal velocity through the liquid is given by this equation. We need to know the terminal velocity. Oh, and they told us a measuring cylinder is filled with a liquid and some steel spheres of different diameters. Okay, so we need a measuring cylinder, the same measuring cylinder which they used, and we'll to measure this length. We can either use graduations on the measuring cylinder, or we could use a meter rule. I would use a meter rule, okay, to measure this length. Then we need a stopwatch, of course. We also need light gates. Why do we need light gates? Well, for accurate measurement. Light gates connected to a stopwatch for accurate measurement of time. Okay, and that's it, I guess. That's all we need. So let's get started. So first of all, we need to draw out a diagram of the apparatus that we are gonna need. So we need a measuring cylinder. Right next to that, we'll need the ruler or the meter rule with its markings. We cannot draw a micrometer screw gauge, so we'll just tell them in the part B about that, but measuring cylinder is needed. And then we've got the steel balls, so we're gonna throw them from here. And apart from that, they are released from here. And this cylinder is filled. Okay, if the cylinder is filled till here, then why is this so low? It should also be high enough to measure the entire length. Okay, we've placed this meter rule. Now what we actually need is, okay, it's better if you use your ruler, okay, to draw all these lines to make them straight. Over here at this marker, we'll attach a light gate connected to a light gate. Just let's label it if we cannot draw it. And at another point as well, there's a light gate number 2. This is light gate number 1. This is to start the stopwatch, and this is to stop the stopwatch. Okay, so as soon as this ball enters, it will have certain velocity, and as soon as it passes through this light gate, the light gate will start the stopwatch, and then as soon as it passes through this length, which will be measured, as soon as it passes through this length and reaches this point, the light gate would stop. Okay, and that's it. Then that will give us the time. This length will already be measured. We can use the time and the length to determine the terminal velocity. Okay. And of course, the ball won't actually reach its terminal velocity. So this might be a source of error as well, because the cylinder's length might not be long enough for in order to allow the balls to reach their terminal velocity. But still, okay, remember one thing, the apparatus that they'll give you, the experiment that they'll give you, if they want you to identify sources of error and they've given you 2 marks for it, this means there are at least 2 sources of error in there, or there might be even more than that, but at least 2 are confirmed in there. So this is one source of error that we could tell them, that when the ball is released, it will initially have a velocity of 0, right? But as soon as it enters, it will start gaining velocity. But as soon as it reaches here, it's not important that it would have reached its terminal velocity, but we are assuming that, yeah, it reaches terminal velocity. The ball might still be accelerating and it might still reach this point, and it might still not have reached its terminal velocity, or it might have reached its terminal velocity somewhere in the middle. So this might be our error in the experiment. And I remember when I was performing the same experiment in the lab, yes, this experiment did actually have a lot of errors. Okay. And second error that we could identify over here is that when we release the ball from up here, it might not go in the center of the, it might not fall in the center of the cylinder, but it might hit the walls of the cylinder. It might rub against the edges of the cylinder, so it might not flow down smoothly and might not experience the resistive forces only due to the liquid, but also due to the sides of the cylinder. So this might be a second source of error that we have. Okay. So this is our apparatus that we have, and also of course label it: meter rule, cylinder, light gates, ball, and that's it. Liquid. The second part says, list additional apparatus that you have not drawn in the diagram or shown in the diagram. So I'll write B over here. Additional apparatus is micrometer screw gauge. Of course, I cannot draw that out in the diagram, and I don't need to draw that out. Micrometer screw gauge. And also light gates, I have not drawn them out. So to be on the safe side, just mention them. Of course, the examiner won't give you negative marks on it, but just to be on the safe side, I've mentioned them. Then part C says, list the quantities to be measured. Okay, so what quantities are we supposed to measure? The length, this length of the cylinder through which the ball falls. So the length through which the ball falls. We also need the diameters or the radii of the ball. So diameter of the ball actually. Diameters of the balls. What else do we need? We need the time. Time taken by the balls to cover that length. Taken by the balls to cover the length. To cover the length L. Is there anything else we need? We don't need the mass, right? Then do we need the mass in here? Well, we don't need the mass. We need this. The density is already known, and velocity will be calculated using the other measurements, the length and the time. Then part D says, for the quantities listed in C, explain your choice of measuring instrument. So the instruments used for these points. So for the length, we can use meter rule. For the diameters, we can use the micrometer screw gauge. For the time, we can use light gates connected to the stopwatch. And that's it. Then after that, we have E says which is the independent and which is a dependent variable. All right, D, then comes E. Okay, for the independent and dependent variables, we'll need to look at this equation now. First of all, identify all the constants in here. Which are the variables and which are the constants? Can you identify them?
The variables?
Yeah, the variables and the constant. Is eta the variable or a
Sir,
constant?
you're lagging.
Hello? Hello?
Yes?
Yeah. Is it fine now?
Yeah.
Okay. Is eta the variable or the constant? Eta
The
is,
variable.
it's a constant. It's not going to change. Of course, that we are not going to change the liquid. Will the viscosity of the liquid change during the experiment?
I don't know.
Yeah, so it's a constant, not a variable. Will G
Okay.
change?
No.
So is it a constant or variable?
Once.
Will the densities change?
Yes, it's a variable.
Why will the densities change? Why will the density of steel and why will the density of the liquid change? Am I converting the steel into some other object? Am I converting the steel into copper or silver or some other material? The densities only change when you change the material. They do not change otherwise, okay? So they are also gonna stay constant. So all these are constants, but the radii, are they changing? Some spheres of different diameters, are the radii changing if the diameters are different?
Yeah.
So is
That's a
that the
variable.
constant? Oh, that's a variable. Shukar. And what about this? Will the terminal velocity change for every ball that we take, for a larger diameter ball and for smaller diameter ball? Will they have different terminal velocities? Definitely. So that's also a variable. I know you were really confused regarding this terminal velocity, that how could it be different? Well, it's different for different objects, okay? Not for the same object. That is what we mean by saying that it can change, okay?
Okay.
Yeah, so now we've got two variables in here. The graph is always plotted against two variables, and the variables are the independent and dependent. The variable written on the right hand side over here, the radii, you can change them independent of this velocity. You can change them by just changing the balls, right? But in accordance to the change in radius, the terminal velocity will change. So terminal velocity is dependent upon the radius. So radius is your independent variable, which you can change. And terminal velocity is the dependent variable that changes because of the change in radius. So it depends upon the radius. Okay? So
Okay.
radius is the independent variable and v, the velocity, is a dependent variable. So just write it right over here. The radius of the spheres, well, let me check out if r is representing the radius. Yeah, it's the radius. Okay, radius of spheres is the independent variable, and what's the dependent variable? Terminal velocity are the dependent variables. Okay, so we need to draw out graphs in between them. And then the F says for one quantity, comment whether repeat readings are appropriate for this in this case or not. Okay, so for which quantity that we have measured so far, should we need the repeat readings? We could either repeat readings for the time and take average. Okay, we could time experiment for the same ball again and again and take its average, or we could repeat them for the radii. We can repeat the measurements for the radii. For instance, if I take one ball, let me call that ball S1. For the same S1, I could measure the radius or the diameter in this direction, or I can do the same measurement in the other direction, or in some other direction. And then I'll take all of those readings and I'll take their average, D1, D2, and D3, and then divide them by the number and get their average. So I can repeat the readings for either the diameter or for the time. Okay. So they want us to write down one quantity, whether repeating readings are appropriate. So yeah, for either For the diameter, repeating the readings are appropriate. Diameter measurement. Repeat at different points and take average. Or you could just do it the same thing with time as well. Or repeat for different, meaning not actually, this doesn't mean you do it for different times. Repeat for the same ball, okay? Or measure the time for the same ball again and again. Repeat time measurement for the same ball or for each ball again and again, and then take their average. Okay, so that's how the measurement is needed. Then after that comes G part, which says explain how the data collected will be used to determine the viscosity. Include a sketch of the graph that you have. Okay, this is the equation that you have, right? We've identified the variables, we've identified the constants. And I told you that the graph is always drawn in between the variables. So the two variables that we have are the V, and is it the R or the R squared? Is the other variable R or is it R squared?
R squared.
It's R squared. Okay. So from this relationship, can we say that this terminal velocity is actually going to be proportional to the square of R?
Yeah.
Yes, it's going to be definitely be proportional to the square of R. So we need a graph of terminal velocity against the square of R. Against R square needs to be drawn, needs to be plotted. So we can draw out a graph of V against R squared, and we know that V and R squared are proportional to one another. So what do you think will the shape of the graph look like? Of velocity, terminal velocity against R squared. And remember one thing, the independent variable is always drawn on the x-axis, okay? And the dependent variable is always drawn on the y-axis. Y-axis has the dependent and the x-axis has the independent variable. So what should be the labeling of the y-axis? Should it be V or R squared?
R squared.
V is the independent variable. Sorry, the dependent variable. Dependent.
We would depend on the diameter.
Sorry?
Yeah.
Velocity does not, we cannot change it. It's the diameter that's going to change it, okay? And the R squared over here is the independent variable. Oh, sorry. Okay. And if R squared is the independent variable and that's the dependent variable, this is the graph, and the shape of the graph is going to be straight line passing through the origin. Okay, because they have a direct relationship. But now that's not the only thing that we need to write. We also have to mention that how are we going to get a value for eta from this graph. Okay, so the equation which they gave us, we can use that to answer that part. V is equals to 2R squared times rho s. Let me copy that over here. 2 times R squared into rho s minus rho L. Rho s minus rho L into G divided by 9 times eta. Okay, we've drawn, oh wait, there's an R squared as well. Oh yeah, it's right over here. Okay, they've written the R squared over here. Okay, instead of writing it here, I'm gonna remove it from here and I'm gonna write it over here. Does this change anything? Does this change anything, or is it still the same thing? Is it still the same equation which they have given us?
Yeah.
Okay, so if it is still the same equation, what is this entire part representing in this graph?
The gradient.
The gradient. Good. So the gradient of this graph will equal this entire constant. Okay, so if it is equal to this entire constant, so how can we find the eta's value? So the gradient is equal to 2 upon 9 times rho s minus rho l into the gravitational constant divided by the eta. You just rearrange that. Okay, rearrange it, take the eta on the other side and bring the gradient down here. So gradient into eta. So this is how you can get the value for eta from this graph. So what you need to do is you need to write the following stuff in there. Find the gradient of the graph, or you need to first mention that draw a graph of v against r squared, plot a graph of v against r squared, then find the gradient, and then use it to find eta by the following technique, and then you're gonna mention this thing over there. Use it to find eta. And how are you gonna do that? Well, eta is equal to, just copy that stuff down here, 2 upon 9 into rho s minus rho l into g, rho s minus rho l into g. Yeah, and then that's divided by, this is divided by the gradient, right? Instead of dividing it by the gradient, I'm gonna multiply this entire constant by 1 upon the gradient. Means the same thing, right? Dividing it by the gradient or multiplying by 1 upon gradient means the same thing?
Yeah.
Yeah, so this will give you the eta. That's how you're gonna find out the eta, by just finding out the gradient and multiplying it with this constant. And this entire constant is already known. They told you that rho s and rho L are already known, and G is also already known. It's 9.81. Okay, so once you've done that, once you found the value for eta, then they're saying identify the main sources of uncertainty or systemic error. So I told the sources of error at the beginning. G के बाद that comes H. Sources of error include, first of all, the ball might not have reached the terminal velocity, might not reach terminal velocity when measuring time. We can also have another source of error, that the ball might not pass through the edges. Sorry, might not pass through the center, not the edges, of course. That is, might slide against the edges. And I guess that's almost, and yeah, we might have error while measuring the length as well. What is that error called? Well, parallax error might be possible, but parallax error usually doesn't carry mark. I don't know if this marking scheme allows it, but these are the two sources of error.
Yeah, it does not.
It does not allow it? Okay. Oh, you've read the marking scheme.
No, but I think so.
Okay, you think so.
Because in most of the marking scheme and like other questions, they don't allow for the parallax error.
All right, but that's actually depending upon the type of experiment. Over here, they should, because see, you've got a meter rule, and when you'll be viewing it.
Can you check the marking scheme?
Wait, after this, after the safety. How can we comment on the safety? Well, you've got liquid oil in there, so if the liquid
safety goggles.
Safety goggles again? Safety goggles everywhere? How can we use? Why?
So it does not splash into your eye.
What? The liquid? The liquid won't splash into your eye if you are releasing the steel balls. I'm using the term releasing. Releasing means you're just allowing it to go with 0 velocity from the surface. So it won't splash at all. So, well, there might be a chance that while filling this, this liquid might spill out. It can spill out, but it won't go into your eye. Okay, so when it spills out, it might deposit on the floor and you might slip on it. So it's better to just mop it out. Okay, this is oil, and oil is slippery. Okay, they didn't tell us anything in the question about the oil, but yeah, liquids usually are slippery. This is actually oil. Well, I did the experiment myself, so I do remember it was oil. But there is no such safety hazard in this experiment at all. When the spheres are going at a slow speed, and so it's better to just mention that part, that liquid might spill on the floor, and the person might slip. Liquid might spill on the floor, so chances of slipping. So what to do then? So mop the floor as soon as the liquid falls on it. So let's now check out the marking scheme. Oh, long marking scheme. Draw and label the diagram showing how the apparatus will be used. Appropriate diagram including 2 markers on the measuring center or 2 light gates. Okay, we did the light gates stuff, so we got that mark. Now list additional instruments which are not shown. Okay, we did show the meter rule. We did show the meter rule on the diagram, but still, stopwatch or light gates, micrometer. Okay, we got all the 3 points. Okay, but any one of them would have been acceptable because it's just for 1 mark. Then list the quantities to be measured. Diameter of the sphere, yes. The time, yes. The distance, yes, between the markers, or the time and distance between the gates, or the time it takes for it to measure that. We did mention that length L, so the time it takes to cover that length L in between the markers means the same thing. We got that mark as well. Okay, now 2 quantities listed in C. Explain your choice of measuring instruments, or quantity and instrument. Indication of precision related to expected measurement. So multiple answers are accepted over here. So the ones which we've written, that's also correct. We've written that the micrometer can use the diameter. Micrometer can be used to measure the diameter. The stopwatch and the light gauge can be used to measure the time, and the meter rule can be used to measure the distance, and that's exactly what they need. Then state which is the independent and dependent variable. Diameter and the time. Allow the radius for diameter and velocity for time. Independent and dependent variables are correct. Okay, so velocity is an independent variable. Sorry, dependent variable. We did identify the velocity as a dependent variable, and we did identify the radius as an independent variable. So we got both the marks because both of them have been allowed. Then for 1 quantity, comment on whether the repeat readings are needed or not. So these are just a few examples. Multiple examples are accepted. That means repeat the diameter measurements at various orientations at average. Okay, we did that. Time, average, and we also did that as well. Time can be repeated and then average. Repeat identified measurements or eliminate the anomalous errors. Yeah, you could do this as well. This is an additional point which I think you should remember, that when you get an anomalous value, eliminate that or leave out the anomalous values and take the average of the rest of them. Okay, remember, usually during the MCQs we get the anomalous values as well. Then explain how the data collected will be used to determine the viscosity, including a sketch of the expected graph. So calculate the velocity of each graph. So you could plot a graph of V against R squared, and we did that, exactly that. Okay, and then we sketch a graph of labeled axes and straight line passing through the origin. We also did that. We did this. Equations to identify it. We did give an equation and the use of gradient to calculate the eta. And calculate the velocity for each sphere, and calculate the radius using each sphere, for each sphere. So we didn't mention this point, so I think we lost this mark. We didn't mention how we can calculate the velocity, or we didn't mention how we can get the radius from the diameter, because of course we can't measure the radius directly. This is one part, 1 point which we lost. Okay, so I would say this is 1 mark that we lost. And then the next part says identify main sources of error and uncertainties. Terminal velocity not reached. See, exactly the point which I told you. Ball not dropped in the center, so eliminate the edge effect. Time to fall is short, so time is significant. Reaction time is significant, which means actually there is a high percentage uncertainty in the time measurement. Diameter is small, so again, large percentage uncertainty. Zero error on the micrometer. Parallax error. See, parallax error has been identified in specified measurement, meaning while measuring one of the lengths. But parallax error, as you said, is not usually a good answer, so it's better to avoid that. But if it is the only answer given, the only type of error which you think is in there, so to go for it, okay? And risk, oh, spills it and mop it up. We got that. And safe experiment, no precautions necessary. So we actually lost 1 mark, and that 1 mark was for calculation of this velocity or for using the diameter to get the radius. Is this question? Okay, so question 8, the last question. Student determine the acceleration of free fall G using a simple pendulum. This is a simple pendulum. And now the pendulum consists of a mass attached to a string, which is suspended from a support as shown over here. This is a string, this is a mass, and this is suspended from a support. The equation for the simple pendulum is given to you. T is equals to 2 pi under root L upon G, where T is time taken for the mass to make one complete swing from A to B and back to A. A length is L is the length of the string. The student recorded the following results. When length is measured in 10 raised to the power of minus 2 meters. 10 raised to the power of minus 2, what does that mean? That means it's centimeters, right? This means the same thing. And then the time has been measured, and then the square of the time has been taken over here. Okay, these are the measurements in centimeters. And this is the pendulum. As soon as it reaches here and then returns back to its original position, we can say that one complete revolution has been performed, or one revolution has been completed. So now, criticize these results. Okay, let's look at the, okay, we've got different significant figures in there, right? So since the significant figures of the raw data are 2, but over here we've got 3 and we've got 1 and we've got 2, and same thing over here. So significant figures are not the same, they're different. Significant figures should be 2. For time and t squared. But over here, they've got 3 significant figures and 2 significant figures and 1 significant figure as well. So significant figures are not correct. So not correct. I think that's the only criticism that they need. Let's verify it from the marking scheme. And by the way, if you remember the previous Unit 3 paper, the same thing was there. And yeah, of course, the same. See, the marking scheme is exactly the same. Small range, only 5 sets, inconsistent number of significant figures, we got this mark. Should have timed more oscillations. Small range was also given in the previous Unit 3's marking scheme. Only 5 sets, no repetition shown. This was also given. Inconsistent number of significant figures. So I would suggest just learn these points, because these will always be repeated, because this is the pattern of this question, the last question. Okay, significant figures are not appropriate. Okay, I'll erase this out and write it down. Non-appropriate significant figures. And then apart from that, the range, no repetitions have been shown over here. The time, he should have measured T1 and then T2 and then taken their average. So no repetitions of time have been shown. And only 5 experiments, 5 sets of data have been recorded. So smaller range of data. This is always repeated in this last question, okay? The first part is always for the criticism of this, for the data or the experimental data that they have given. Explain why the graph of t squared on the y-axis against L on the x-axis should be a straight line passing through the origin. Why would the t squared against L be the straight line? This will only be a straight line if t squared would be proportional to L. So let's look at this relationship that they have given us. If we square this entire formula that they have given us, t is equals to 2 pi under root L upon G, if we take the square of both the sides, So what would it become? It's going to become 2 squared. T squared is equals to 2 2s are 4. Pi squared, and the square root will cancel out. So it's going to become L upon G, right? This is what it will become if we square both the sides. So looking at this expression, the 4 pi squared and the G are a constant, right? So since 4 pi squared upon G is constant, can I say that the T squared is actually proportional to L? And if that's proportional to L, see L is in the numerator and T squared is over here, they're proportional because this part is constant. Then if they're proportional, it's going to be a straight line passing through the origin. See, easy. Through origin. And then the next part is for 5 marks, drawing it out on the graph and a line of best fit. Oh, sorry about that. Okay, so again, you have to be very careful about the scale that you choose. The y-axis and the x-axis scale that you choose, it must cover at least 90% of the data. But before you choose the scale, you first write down the correct number of significant figures for your data. So this is going to be 1.1 only. Okay, 2 significant figures, 1.1 again, 1.0, 1.0, 0.91 is correct, and 0.80. Then over here, 1.3 is fine. 1.3 should be written, 1.1, 1.0, 0.83 is fine, and 0.64 is also fine. And now we need to plot a graph of, we need to plot a graph of T squared, this thing, against the L. Okay, so let's draw this from 20 to 40, and the L and the T. The L is on the x-axis and the T squared is on the y-axis, as they've told us. Yeah, T squared is on the y-axis and L is on the x-axis. Okay, I told you the rules of writing down, of labeling the y-axis, because these also have the marks. A T squared is going to be written, and then you have to put a slash and then write down the unit of T squareds. What's the unit of T squared? Give me the answer, please. What's the unit of T squared? What's the unit of T? Is it second?
Second square.
Yeah, it's second squared, correct. Okay, so T squared slash second squared has to be written over here. And I think that's exactly what they gave us over here. And over here, the unit is going to be raised to the power of -2 and meter. Okay, that's the unit. So you have to label that as well on the x-axis. L and raised to the power of -2 in meters. Okay, if you don't have space, do not go out of the boundary. Of course, they've told, you might be knowing this, that you cannot write beyond this boundary, right? So just bring it back inside. Okay, where did it go? You know that, right? You cannot write beyond this boundary. This is going to be length in 10 raised to the power of -2 meters. Okay, do not write beyond this boundary. Okay, it won't be checked. You know that, right?
Yeah.
Okay. Then once that is done, the time has been labeled, a length has been labeled. Now choose appropriate scales. It's not important to start from 0. You can start from any number you like. Okay, we've got from 20 to 40. Actually, but the number should be such that it should cover most of the scale. So on the y-axis and on the x-axis. On the x-axis, we are starting from 20 and going to 40. So let me zoom in now. If I'm starting from 20 and 30, 40, so this is going to be very small. Whereas if I start from 22, 24, 26, 28, then 30, 32, 34, 36, and then it will only go to 38, still small. Actually, it's too large now. So if this is 20 and I take this as 22, then it's going to be 24. Then this one is 26, 28, and now 30. So 32, then 34, then 36, then 38, and then 40 is over here. How much have I covered the graph? 1, 2, 3, 4, and 5. Still 50% only. This should be more than 50%. Still the graph isn't good enough. So 21, 22, 23, 24, 25, 26, 20, then 25 and 30 is not good. 20, 25, 30, 35, and 40. 20, 22, 24, 26, 28, 30, 32, 34, 36, 38. Okay, so
Yeah.
this is your best fit line that you get with the points very close to the line, and try keeping the number of lines above and below, the number of points above and below the line equal. Okay, and so this completes this part, and then moving on to the next one, which says determine the gradient. So for the gradient, you have to keep the points that you choose for the gradient, they should be as far apart from each other as possible, so as to cover most of the uh, so as to cover at least 90% of the graph. So let me choose the gradient. First point should be somewhere over here, then the second point should be somewhere over here, and then these 2 points are used to determine the gradient. Okay, you have to draw the triangle as well, and the triangle must be drawn perfectly. Okay, it shouldn't be going like this way. Okay, it shouldn't be this way, it shouldn't be the way I have drawn it right now, but it should be very perfect. Okay, it should be passing the lines and then connecting the 2 points. The triangle also has the marks. Okay, and then the triangle should be covering most of the graph to get the gradient. And then after that, what the examiner is asking you, just a sec. Now once you have the gradient, use the gradient to calculate a value for g. Okay, so for calculation of g, you've been given something in the beginning. Remember, 2 pi t squared is equal to 4 pi squared into L upon g, right? This was the equation that we came upon. So 4 pi squared upon g is your gradient. They need a value for this g. So you just calculate the gradient from here, plug it in here, get the value for g. Rearrange this equation, it's going to be 4 pi squared divided by the gradient, and you'll get a value for g over here. Okay, and now percentage difference from the g value calculated in part 3 and the accepted value of g. Okay, your accepted value of g is 9.81, which you already know, right? Meters per second squared. This is accepted value of g, and let's assume the value that you have calculated over here is, let's say, 9.71. Okay, just giving you a value over here. Now we need a percentage difference in between them. So percentage difference actually means just take the difference divided by the actual value multiplied by the 100. Okay, so their difference is going to be 9.81 minus 9.71 divided by the actual value, which is 9.81, multiplied by 100%, and this will give you your final answer. Get it?